workshop, and I enjoyed it very much. So today my talk is going to be based on joint work with a longtime collaborator, Tony Kai, on detection of sparse signal segments. So the basic problem I'm interested in here is very simple. Suppose you have observations on a long sequence, and most of the sequence is actually just a pure noise. But you have small segments of signals embedded in this sequence. And my goal is to detect these signals. So the basic question is, to what extent and how can we effectively detect these signals? The key difference with the usual sparse signal detection problem is, well, here, instead of just having singleton signal, the signal actually comes in as segments. So you want to take advantage of the structure in the hope that you can detect the signal better. But similar to the usual sparse signal detection problem, we still, because the segment length is much smaller when compared with the original sequence, so you still need to deal with the multiple testing problem. Of course, this kind of problem naturally arises in many different applications. Here, I just want to give you a couple of examples in a very superficial way. So one of our motivating examples is this so-called copy number variation analysis. So the basic idea here is if you look at the whole genome, you are going to see many changes, either due to mutation or deletion. The usual single nucleotide polymorphism basically look at the changes at a single base pair. But in this kind of copy number variation, what we are interested in actually is a segment of changes. And we want to find these segments, and there are several ways that nowadays you can do this. And typically, the data you would observe in a very typical study is given in the top panel here. So what we have is the x-axis basically is the relative location on the genome divided into different chromosomes, and the y-axis is the log ratio of the copy number you observe on a particular genome compared with the reference genome. So as you can imagine, if there is a low change, what you would observe essentially is a pure noise with a mean zero. But if there is a change, what we are going to say is a significant deviation from zero. But of course, the main issue here is if you just look at the top panel, it's very hard to say what the signal is, whether or not there is any segment structure. But if you zoom in to look at a particular chromosome, or even a particular section of the chromosome, as the bottom panel shows, it's pretty evident you see right in the middle, like right here, you would have a segment of changes. And here, as you can tell, the two main features, as I mentioned before. First of all, it's not a singleton signal, but rather a segment here. The segment in this particular case lasts about 200 base pairs. But when compared with the whole genome, this is still a very short segment. And another example, probably is more generic, is a peak detection problem. So basic idea here is, suppose you observe a signal, can you identify all the peaks in this signal? And this particular data example actually is taken from the so-called ChIP-seq data analysis. Really is a way for biologists to identify the so-called transcription factor binding sites. And each of these sites would correspond to the peak, basically in the top panel of this figure here. And of course, when you just look at the top panel, you may think that the peak really is just a single change at a single location. But for example, if we zoom in to look at the peak right here, you realize actually the peak lasts for about 200 positions. So again, you would have a segment of changes. And this is very important. Well, this may not be very important for detecting, say, for example, these sharp peaks, because the signal is strong enough. But this is much more important. Suppose you have a relatively weaker signal. You want to really share information together by recognizing the fact that the signal actually comes in as a segment. So mathematically, how do we formulate this problem? It's actually a very simple model here. We look at this, so this basically a signal plus noise model. Suppose your observations are xi, which is, again, as I mentioned, is a very long sequence. Suppose the length is n here. And signal detection problem we are considering here essentially is a hypothesis testing problem. So under null hypothesis, there's no signal at all, so all the means mu1 all the way to mu_n are all zeros. But under the alternative, just for simplicity, let's just start with just one segment of signal. So that basically means there is a segment, basically an interval between 1 and n, where you have a signal embedded to it. So here I'm going to represent this signal by this Fn here. So you can think of this Fn essentially as a function defined between 0 and 1. I kind of either stretch it or squeeze it so I can put it in a long sequence. And the goal here, of course, is to understand, as I mentioned before, to what extent we can detect such a signal. And very intuitively, we probably would realize there are two main determining factors on the detectability of the signal. One is its amplitude. The other one is duration. Just to give you some ideas, let's look at a very simple exercise here. So the signal I have here is on the right-hand side. It's of this shape. And what I do here is a very simple simulation study. So I embed this signal into a sequence of length 2048. I embed them right in the middle section here, which lasts exactly 200 positions. So what I have here is in the top panel and the bottom panel essentially is the difference of amplitude. Well, of course, the signal actually I highlighted here using this red box. If I don't draw this red box, it's much harder to say whether or not there is a signal in the top panel. But in the bottom panel, by increased amplitude, it becomes much easier to find this signal. Similar story for the duration. Again, if I insert this signal into the middle of this sequence, the difference between the top one and the bottom one is the top one lasts only for 100 position, while the bottom one lasts for 500 position. Again, as you can tell, it's much easier to say that there is a signal in the bottom panel. So of course, this gives us some intuition that when the amplitude of signal is larger, it's easier to detect. When the duration is longer, it's also easier to detect. But what we're interested in is exactly what kind of nature is the relationship between the two, so we can detect the signal. And it turns out it depends on how much you know about the signal. So in this particular case, we look at 3 different situations. The first situation is suppose you know the shape of the signal. So you don't know the amplitude, you don't know the location, but you know exactly what kind of shape the signal has. The second situation is suppose we know nothing about the signal. We don't know the shape, we don't know anything about the signal. And the third one is perhaps more realistic. Suppose we have a little bit quantitative information about the signal. How much better can we do? So let's start with the simplest one. Start with the situation if we know exactly the shape of the signal. So basically, this signal Fn here is just a constant multiplied by a long template, F0 here. And the most well-studied case, actually, there have been some study of this particular setting, essentially, probably starting with Ariel Castro in 2004. So they look at the case, suppose this F0 is just a constant. So suppose you have a constant signal, how do you detect the signal? And then they study the so-called scan statistics, basically the likelihood ratio test in this case. And of course, there's nothing special about the constant signal. You can naturally extend their result into any arbitrary, but you have some regularity conditions for sure. So you can extend this to more general long templates. So basic idea here is if you look at a particular window, suppose I want to ask myself a question. If there is a signal between AN and BN, so what I'm going to do is I'm going to look at the weighted average of your observation in that window. Because the main reason is because I know the shape of the signal. If there is indeed a signal, I want to choose a weight accordingly, basically reflecting your knowledge of the true signal. I look at this weighted average, and of course this is only for one segment, one window here, and I move across all possible or candidate segments. So for each segment, I ask myself a question, if there is a signal or not. And I take the maximum of all these statistics and reject the null hypothesis, of course, if this maximum it goes beyond a certain threshold. And turns out you can show, indeed, if you choose your cutoff point or threshold critical value appropriately, basically is over the order of square root of log n, then you can detect any signal that satisfies this condition. So basically, this sign implies I have larger than or equal to up to a constant factor here. So the squared amplitude is going to be greater than or equal to up to a constant of the order, basically is log n over dn. So log n is the length of the original sequence, and dn is the length of the real signal. And I just want to demonstrate a little bit on how this really works. So suppose again, so this is the figure actually I showed you before. So now if I don't draw the red box, probably you find it's a little bit harder to say whether or not there is a signal or not. So I look at a different window. So I look at in the simulation I did many different window sizes, but here, just for illustration, I focus on 3 different window sizes. So this one is 20, this one is 100, this one is 500. So what I do is I slide this window. For each window, I calculate this likelihood ratio statistics. And these are the plots of these statistics. And one thing I want to emphasize here is our test procedure essentially takes the maximum of all these test statistics. And if you look at just these 3 panels, what I can tell you is if you look at the window of size 20 or window of size 500, which of course is different from the truth in this case, you won't be able to detect the signal. But if you have the right size here, not only you are able to detect the signal, you can locate exactly where the signal is by taking the maximum of all these likelihood ratio test statistics. And it turns out, with a little bit of calculation, you can also show this would be the best you can do. In the sense that you can, if the signal really has the amplitude satisfy this condition, then as I mentioned, the likelihood ratio test statistics can achieve consistent detection, meaning that if you sum up type 1 error and type 2 error, it goes to 0. On the other hand, following the language of Castro et al., if the amplitude of a signal actually is smaller than or equal to this order, well, actually up to a constant here, smaller than or equal to this, any test would be powerless. So basically, there is low detection scheme that would be able to detect such a weak signal. So one issue I want to emphasize here is from this rate, actually, you can immediately see the benefit of recognizing the fact that a signal comes in segments. Because if you only have one singleton signal, the detection is only possible if you see a very large observation. How large? Basically, you want that observation to be of the order log n. But if your signal really is a lot sparse, actually goes over a long region, say, for example, dn is of the order of the whole sequence, it's just a fraction of a sequence, detection is possible if you have even very weaker signal. So again, as I mentioned, this is perhaps the simplest case where we assume that you know the shape of the signal. And in most practical cases, that's probably, such information probably is not available. So at the other end of the spectrum, what we would be interested in here is, well, what happens? Okay. Thank you, Richard. Yeah, so what would happen if we don't know anything about the signal? So the signal can be of any shape. I don't have any prior knowledge. Clearly, you can no longer play the same game as before, because what we did before essentially is averaging out your observation in a particular window. Now, if you don't know anything about the signal could be positive, could be negative. If you just do an average, you will average out the signal. Turns out a very simple trick will essentially solve this problem. So what we do is, instead of looking at the average directly on the original observation, I take a square of all the original observations and then average them out. But one thing you got to pay attention to is, because I have noise, when you square, you have to center it. So essentially, I subtract the mean when you just have pure noise and then average them out. Another issue I want to emphasize here is, instead of normalizing just using the length of the signal, you also want to account for multiplicity. So here is this factor of log n comes into play. And then I essentially play the same game. I look at all candidate windows. For each window, I calculate this quadratic test statistics. And then I look at the maximum. If the maximum is greater than a critical value, I'm going to say there is a signal, and particularly the signal is located at the maximum point. Yes? Well, the intuition is just as I mentioned, because your signal can be positive and negative. If it's just one sign, you probably will think about just averaging them. And the main difficulty of averaging them is if you have positives and negatives, you will average out the signal. By doing square, you would keep the signal essentially. Well, I'm assuming that you don't know anything about the shape. So unlike the previous one, you know exactly what the shape is. Any other questions? Okay. So again, yes. I'm still assuming that the signal is just in one interval. But this can be relaxed, and later I'm going to talk about how to kind of change this a little bit so you can detect multiple intervals. Any other question? Okay. So again, we are just focusing on one signal segment, and if you don't know anything about the signal, you do this kind of quadratic type of statistics. And you can also show, again, you choose the critical value to be of the order of square root of log n, then you would be able to detect any signal if its amplitude is greater than the sum of two things. The first thing is exactly the same as we've seen before for signals where you know the shape. The second thing is extra. Actually, this is just an alternative way of writing the following thing. Basically, is wide or not, knowing the shape of the signal helps you. Really depends on how long your signal is. And of course, this is just in terms of the rate, not in terms of constant. In terms of constant, certainly knowing the shape will help a lot. But in terms of the rate, there are actually two interesting regimes. For short signals, you still have detection at a rate essentially log n over d. But for longer signals, all of a sudden you need to take a square root, which means you are going to ask for much stronger signal so that you can detect it. And you can also show this indeed is the optimal rate in that any other detection scheme would become powerless if the amplitude is of order, or is smaller than or equal to this value here. And the most difficult case, well, for those who study this kind of minimax lower bound stuff, you want to know exactly what kind of signal is the most difficult to detect. The most difficult signal to detect essentially is your signal that flips signs very often. So basically it's random plus or minus this amplitude here. And I wanted to again emphasize a little bit about the comparison between the case where you load the shape and where you don't have any information about the shape. So again, as I mentioned, as far as the rate is concerned, for shorter signals, you don't lose much by not lowering the shape. But for longer signals, lowering the shape really helps you tremendously. And just to, again, give you a little bit of intuition on how these two situations compare with each other. Again, I look at this example we've seen before. I have this signal really highlighted in this red box here. So the red dots is the case when you load the signal, you do scan with this linear statistics, and the black ones correspond to the quadratic type of statistics when you don't know anything about the signal. I scale the two so they can have the same critical value. And the critical value would correspond to this horizontal gray line here. So what surprisingly is we've already seen before, if you load the shape of the signal, you will be able to tell that the signal is right here. As you can tell, this is a very good identification of where the signal is. But if you don't know the shape of the signal, you will just fail to identify the signal because this is just below the threshold. So what this tells us is exactly lowering the shape of the signal really can help you in situations like this to detect the signal. But the very natural question here is, how much does it take for us to fill in the gap? Because in practice, it's probably too much to ask to say that we know exactly the shape. But maybe we don't just, but on the other hand, it's probably a little bit too pessimistic to say that we don't have any information about the signal. And it turns out, if you know a little bit qualitatively about the signal, it can help you a long way. And in particular, we look at this specific situation. Suppose you know the signal has some sort of smoothness. And to describe the smoothness, here we use the Holger class. Essentially, what we are looking at is, suppose you know a little bit about your signal. Essentially, your signal should come from a Holger ball with an order alpha. And here, naturally, there are two questions. The first one is, in this case, what's the optimal detection rate? The second one is, how do we devise an effective tool of finding or taking advantage of the smoothness and better detect the signal? And turns out we have all the main ingredients already in the previous two cases. But here we need to combine them a little bit. The main intuition here is, here we scan, in the case when we load the signal, we do some sort of linear statistics for scan. If you don't know the signal, you do quadratic statistics. And the linear statistics turns out to be very good. Suppose your signal does not change very much with respect to information about the signal, but the quadratic statistics is very useful. Suppose your signal changes dramatically, very quickly, and you want to combine these two together. Well, before we talk about the details about this, I want to just kind of show you this diagram, essentially demonstrate what kind of main detection rates, what kind of main result in terms of optimal detection rate we would obtain. Turns out it's a very peculiar setting here. So what we have seen here, well, what I plot here is the x-axis is the length of the signal taken, well, scaled with log n. So basically, you can think of the length of the signal is log n to some polynomial, and this would be the degree of the polynomial. Same thing, I look at the look at the amplitude of the signal. If I look at this as a polynomial of log n, here this would be the degree of the polynomial. So from our previous discussion, we know that if you load the shape of the signal, basically the detection region is anywhere above this diagonal, so including all these shaded areas. And we also look at a situation when you don't have any information about a signal. And the latter would correspond to essentially to this quadrilateral area shaded in red. So this is the area where you can detect the signal even without information about the shape. So what happens if you have a little bit of smoothness? And turns out there are two different situations. Here I just give you two examples. One is suppose I know it's smooth in that the signal comes from a Holger class of order 1. Then this would be, again, this quadrilateral area shaded in both red, yellow, and blue. But if it's from a Holger class with order, say, in this particular example, 1/5. All of a sudden, this becomes essentially a pentagon. Essentially would be the area corresponding to both the red shaded region and the yellow shaded region. Actually, this is a long convex pentagon. Here you have a kink here. So this is basically the main kind of a summary of the main result we would get. Now let's talk a little bit more detail on exactly what's the nature of this diagram here. Let's start with the question, how do we detect the signal? By taking advantage of the smoothness. The strategy, as I mentioned, actually is very simple. We try to combine the idea of linear statistics and quadratic statistics. So to start off, what we are going to do is we are going to suppose we are interested in knowing whether or not there is a signal between AN and BN. So I would start off by dividing this interval into several bins. And within each bin, because of smoothness, the signal is going to be more or less stable. So then I do average within the bin. So this is how I end up with this average is what I call YJ. Of course, you scale it a little bit so they can have some sort of more or less normal distribution with some variance. And then what I do is across bins, because the now signal could change very dramatically. So what we want to do is we want to kind of combine all this information together using the quadratic type of statistics I discussed earlier. And again, this is exactly the same, just about same as before. It's just now, instead of looking at the original data, I look at the average of all the bins. I put all of them together. Again, this would be my evidence for whether or not there is a signal between AN and BN. Then I look at all candidate segments. I take the maximum, and I use the same thresholding level as we've seen before, and then we can detect the signal. But of course, there's one big piece missing here. How many bins should we divide this region into? And this turns out to be a little bit sophisticated. And this is where the kink we've seen in the previous diagram comes into play. It turns out there is a transition. Really, when we look at the signals that are from Holger-Ball, it depends on the order is greater than 1/4 or smaller than 1/4. And of course, if you think about the Holger-Ball, if this order is very close to 0, basically it means your signal is more or less like an arbitrary signal. And if alpha is bigger, of course, it gets smoother and smoother. And let's start with a situation when alpha is greater than or equal to 1/4. They are essentially, well, it's essentially illustrated by this solid black line here. There are 3 regions. The first one is, suppose the length of the window you are looking at is very short. Short in that the length is actually smaller than or equal to log n. Basically, in this case, you don't do any binning. So you just do this quadratic type, which is a lot surprising because as we've already seen, when you do this kind of quadratic type of scanning, basically you don't lose in terms of rate of detection, and you don't lose any information. And the interesting part actually happens in the middle. So at one end is your length is log n, the other end is log n up to an order of 2 alpha plus 1. In this area, forget about how long it is. I'm always going to divide it into bins of size log n. And then, if the signal is even longer, now I want to take into account the length of the signal. So the good news here is, at least for most of the examples I'm going to look at, actually length is more or less fall into this category. And this tells us we don't need to worry too much about how to choose the bin size. Basically, I divide everything into bins of size log n. And in the case when alpha is smaller than 1/4, turns out there is one more change here. So basically, you go up just like in the case when you have alpha greater than or equal to 1/4, and then you take this fixed size of log n, but then the next one actually is the same. I will go up, but then at some point, I'm going to just stay with dn. And this is not surprising either. So basically, what this means is when your signal is long enough, how long? Basically, if your signal is of this order, again, what I'm going to do is I'm not going to do binning at all. So I'm going to just do individual quadratic test statistics. When this choice of the binning size, you can identify the rate of detection using this particular detector, what kind of signals can we detect. Again, of course, not surprisingly, we would have essentially 2 different regimes depending on how big your alpha is, the order is. If the order is greater than or equal to 1/4, you have 2 phases, not surprisingly. So you have a change. Essentially, when your signal is small, is short, then you achieve the same rate of detection as if you know the shape of the signal. But I want you to draw a little bit of comparison with the previous setting when you don't have any information about the signal. The transition occurs at log n. And if you have smoothness, the transition occurs at log n up to 2 alpha plus 1. So the smaller the signal is, I'm able to push actually the range a little bit further. So if the signal is really smooth, what I can do is I can achieve the same type of rate of detection, and even by looking at a little bit longer signals. And when your signal is kind of longer, then you end up with a rate that kind of compounding both things. One is the smoothness, and the other one is basically the log n factor accounts for the fact we're looking at multiple segments. When alpha is smaller than 1/4, this is exactly why we say a little bit of kink here. So basically, I would have 3 different regimes, this area, and then this area. So that would correspond to 2 different transitions, just like when alpha is greater than 1/4. For the short signal, I don't lose in terms of rate of detection. In the middle part, I'm going to gain by lowering that your signal is smooth, although the smoothness actually is very weak, it's smaller than 1/4. But when your signal is very long, there's no benefit of lowering that your signal is smooth. Essentially, you end up with the same type of rate of detection as if you don't know anything about the signal. And this probably is a little bit surprising because the main reason is you lower a little bit of smoothness, and you would expect for longer signals, you should be able to take advantage of that. But it turns out the main issue here is because your smoothness is so weak, and for very long signals, taking advantage of such smoothness becomes more difficult, particularly when you take into account that you are doing this kind of multiple comparison. So again, just to demonstrate a little bit, how much does binning help? Again, I look at this example we've already seen many times here. We have a signal here, and just as before, I have these red dots, probably a little bit hard to say. This is the case. Suppose you know the shape of the signal, so you would use this to detect it. And then the black one, of course, is completely overlaid here, but just if you remember from previous discussion. So the red dots would exceed the thresholding line by identifying where signal is. The black one, where you don't assume you know anything about the signal, which is just below the thresholding line, so you won't be able to detect the signal. Now, suppose I know the signal is smooth. Just as before, as I mentioned, I'm going to choose a bin size, which is just log n. In this case, it's 7. So I look at this, I bin everything into, for each window, I bin them by size 7, and again, within each bin, I average them out, and I cross bin, I'm going to do this kind of quadratic test statistics. And the test statistics is given in these green dots. And as you can tell here, even with a little bit of information about the smoothness, we're going to achieve almost the same level of detection in this particular example. And this is what we often observe in practice. A little bit of binning really helps a lot. So far I've been talking about essentially 3 different settings of detecting just one single signal segment. Basically, it's the case you know the shape of the signal, the case you don't know anything about it, and then the case you know the signal is smooth. But one question you may have, particularly regarding the last one, is you have to choose this binning size kind of carefully if you really want to have a very complete characteristics. You want to choose this binning size according to the knowledge of alpha. And of course, in practice, you want to know how many times differentiable a signal is. But turns out this is not a big problem. And what you can do is you can achieve the adaptation by doing this so-called multi-scale scan. So what you do is, well, it allows shell, basically this is what happens. Suppose, again, I have this window. I want to know if there's a signal. If I know the signal is alpha times differentiable, I'm going to use the test statistics I introduced before. If you don't know how many times differentiable it is, I simply take a maximum over all these possible alphas. And of course, you would think, well, it's taken over all alphas. How do you compute this? It turns out because of discrete nature of the sequence, it's actually not that complicated. Essentially, you are just binning everything at different sizes, and you apply the same type of idea, look at the average of the bin, look at the quadratic statistics, and essentially it's kind of like you are looking at essentially what this corresponds to is I have the original sequence. What I'm going to do is I'm going to do scan of quadratic statistics. Then I'm going to bin everything into size of 2. I do this kind of quadratic statistics again. I bin everything into size 3. I do it again. Actually, in practice, you don't even need to do 2, 3, 4, 5. You can have a factor here. And then you look at the maximum of all these different test statistics. And again, you can show, indeed, if you cut at exactly at the level of square root of log n, you can detect the signal without knowing how smooth the signal is. So this is one practical issue. And another practical issue actually also arising in the previous, well, in one of the questions before, basically is how do we handle multiple segments? Actually, the notation is a little bit complicated here, but the idea is very simple. So basically, this is what we do. We first start by having a collection of all candidate intervals. Then what I'm going to do is I'm going to do a scan over all these intervals, computing the likelihood that there is a signal in any one of these segments. And I take the maximum one. If the maximum one is below the threshold, of course, that indicates there's no signal at all. But if the maximum is greater than that, I'm going to look at a subset of all these whose likelihood ratio, or whose test statistics is above the threshold. And what I'm going to do is I'm going to take the largest one. Once you take the largest one thing you need to pay attention to is all these segments, candidate segments, they overlap with each other. So what I'm going to do is I'm going to take out from the set of candidate segments all rows that overlap with the one I identified. And this makes sense, because the other ones may still show up simply because they overlap with the true signal. So after I do that, I do my scan again, I find the next one, I iterate this, until at the end, you won't find any significant segments. And this would be my collection of signal segments. And you can show under appropriate conditions, this procedure indeed can detect all the signal segments that are detectable in the sense that, as I discussed before, for single segments. Because if the amplitude is too small, you won't be able to detect it. But if you use this scheme, you can detect all those detectable signal segments. And the collection actually is consistent in the sense that all the identified segments would be exactly the segments you want to look at, where the signals are. So I'm not sure if I'm too quick. So anyway, so this is just a kind of quick summary of what I discussed earlier. So basically, as I demonstrated here, detecting sparse signal segments is common in many applications. And it's very important to recognize this because, of course, detection of sparse signals has received a lot of attention in recent years. But the main difficulty when detecting generic sparse signals is you really have to observe something that's really large for you to be able to say that there is a signal here. If the signals comes in segments, it's very important that we share information, taking into account the fact that they are coming into segments and share information within the segment. And this way, this can help us better identify the signal. As you can tell here, even if the information that you can share is very weak, like in the case when you don't know anything about the signal. So basically, the only thing you would know is just their contiguous sites that have signal, but you don't have any other information. Even in that case, there are ways you can share information across sites within a segment so you can have a good detection. And the rate of optimal detection can be achieved essentially, as I mentioned here, basically using the idea of scanning. And the scanning, using what type of statistics to scan heavily depends on how much knowledge you have about the signal. So again, as I mentioned here, there are two main ingredients. One is to scan using this type of linear statistics, which is very useful in the case, suppose you know the shape of the signal. And then there's this kind of quadratic type of statistics, which allows you to accommodate the case when the signal actually changes very frequently. And you can combine both to take advantage of possible smoothness. And actually, there are other settings you can look at, other type of different shapes and things. This kind of prior information oftentimes can go a long way. And also, as I mentioned, the two possible extensions that are maybe of practical interest. One is, suppose you don't know the degree of smoothness, you can achieve adaptation by doing this multi-scale scan. The other one is you can modify the procedure a little bit for you to identify all the possible signal segments. And with this, I'll stop. If you have any questions, I'll be happy to take it. Yes. A very good question. So what he was asking is, what happens if you use some sort of wavelet procedure to achieve adaptation? Actually, there are two issues here. One is the difference between estimation and testing. the rate you've seen here actually is better than estimation. The adaptation result mostly for wavelet actually concerns with estimation. For testing, actually, you can do better. There are signals you cannot estimate, but you can detect. And so, well, in terms of adaptation, typically, when you look at the long parametric regression, when you try to achieve adaptation, you need to pay a price, which is log n factor. And here, not surprisingly, interestingly, you don't need to pay that price. The main reason is that price is compared with the multiple testing factor. That price actually is smaller. So it turns out all the price you need to pay is already in the multiple testing part. Sure. So the question really is the relationship with the detection rate we have here compared with what the INSTA has done. So basically, what the INSTA does is to look at the situation, basically it's in long parametric smoothing setting. Suppose you have a signal between 0 and 1, which is smooth function. How well can you test whether or not the function is 0 or not? And basically, if you are, well, for those who are familiar with this kind of calculation, this is kind of like, well, maybe we should say this. So to do a fair comparison, probably we should look at the situation. Suppose we know exactly where the signal is. That would be exactly what the problem INSTA was looking at. And the rate you typically get, regardless of the smoothness index, so there's a low transition when alpha equals to 1/4. You always get this rate, which is dn up to minus 4 alpha divided by 1 plus 4 alpha. And here the key difference is because you want to account for multiple testing. And what would happen is, one, you have this transition at alpha equals to 1/4. Two, the price you pay for multiple testing is no longer log n, but log n up to some factor that's actually smaller than one half. Yes. Could you say that again? Sorry, I couldn't hear you.
So right now, in the alternative, you have one signal somewhere.
Yeah.
You could imagine the case where you have multiple signals.
Mm-hmm. Mm-hmm. Oh yes, actually, this is exactly what we talk about towards the very end. Of course, I hide some. Well, I didn't discuss much of the details. So basically, if you have multiple signals, actually, you do need some condition for you to be able to tell them apart. Because you don't have much assumption about a signal. You may very well have a signal that goes up, go back to 0, then go up again. So in this case, it's not identifiable. You cannot say if this is one signal or two signal. So basically what people would do in practice is, we're going to say that the signal, the length of the signal is relatively short when compared with the interdistance between signals. In that case, what you can do is by just kind of doing this scan, take out all these intervals that overlaps with what you identified, then do scan again. Just by using this iterative procedure, you can identify all the signal segments.
So you don't have an issue with the union part, because if you scan all of this small intervals,
No, you won't. The main reason is because in just scanning for one interval, you already apply the union bound. Because having two intervals or having one intervals, again, you are just scanning through all of them. And the factor is already the price you pay for scanning multiple segments is already reflected.